In the world of statistics, there are many tools at our disposal to help us unravel the mysteries hidden within data. One such powerful tool is ANOVA, short for Analysis of Variance. This method allows us to go beyond simple comparisons between two groups and delve into the complexities of multiple group comparisons. Imagine wanting to compare the effectiveness of 3 different types of teaching methods on student performance. ANOVA provides the statistical framework to analyze such scenarios, making it an invaluable asset in research across various fields. From healthcare to marketing, psychology to finance, ANOVA plays a crucial role in helping us make sense of data. It allows researchers to determine if there are statistically significant differences between the means of 3 or more groups. This ability to handle multiple groups simultaneously makes ANOVA a much more efficient and informative approach than conducting multiple t-tests, which would quickly become cumbersome and increase the chance of errors. Imagine a scientist exploring the effects of different fertilizers on plant growth. ANOVA would allow them to analyze the growth rates of plants treated with various fertilizers, providing insights into which fertilizer yields the most significant growth difference. Similarly, a market researcher could utilize ANOVA to compare the effectiveness of different advertising campaigns on product sales, leading to data-driven decisions on campaign optimization. In essence, ANOVA acts as a powerful lens through which we can scrutinize data and extract meaningful insights. Its ability to handle multiple groups, coupled with its robust statistical framework, makes it an indispensable tool for researchers and analysts seeking to understand the complexities of group comparisons. ANOVA, or Analysis of Variance, is a statistical test that allows us to compare the means of 3 or more groups. It helps us answer questions like, are there any significant differences in average height between people from different countries? Or do different marketing strategies lead to significant variations in sales figures? ANOVA provides a structured framework to test these hypotheses and determine the statistical significance of any observed differences. The core principle of ANOVA lies in partitioning the total variation in a dataset into different sources of variation. It assesses how much of the total variation is due to differences between the groups, between group variability, and how much is due to random variation within each group, within group variability. By comparing these 2 sources of variation, ANOVA determines if the differences between group means are statistically significant or merely due to random chance. Imagine you're comparing the exam scores of students taught by 3 different teachers. The total variation in scores would encompass all the differences in individual student performance. ANOVA would then separate this variation into 2 components: the variation within each teacher's class, due to individual student differences, and the variation between the classes, potentially due to the teaching methods of each teacher. By analyzing these components, ANOVA helps us understand if the observed differences in average scores between the 3 classes are large enough to be statistically significant, or if they can be attributed to random variation within each class. This ability to differentiate between systematic differences and random noise makes ANOVA a powerful tool for drawing meaningful conclusions from data. When dealing with more than 2 groups, it might be tempting to resort to multiple t-tests. However, this approach quickly falls apart due to several critical drawbacks. Firstly, conducting multiple t-tests inflates the type 1 error rate, which is the probability of falsely rejecting a true null hypothesis. Each t-test carries its own risk of a type 1 error, and as the number of tests increases, so does the cumulative risk of making a false positive conclusion. ANOVA elegantly circumvents this issue by performing a single test to compare all groups simultaneously. This keeps the type 1 error rate controlled at a predetermined level, usually 0.05, ensuring that any significant findings are not merely due to chance. By analyzing all groups together, ANOVA maintains the overall integrity of the statistical analysis and provides more robust conclusions. Furthermore, multiple t-tests fail to capture the overall picture of group differences. They only provide pairwise comparisons, neglecting the potential interactions and patterns that might exist among all the groups. ANOVA, on the other hand, considers the entire dataset and can detect more complex relationships between groups, leading to a more comprehensive understanding of the data. Consider a study investigating the effects of 4 different exercise regimes on weight loss. Multiple t-tests would only compare 2 exercise regimes at a time, potentially missing out on the combined effects or interactions between different regimes. ANOVA, however, would analyze all 4 regimes simultaneously, providing a holistic view of their impact on weight loss and potentially revealing more nuanced findings. At the heart of ANOVA lies the concept of partitioning variance. The total variation within a dataset, represented as the total sum of squares, SST, is divided into 2 main components: the sum of squares between groups, SSB, and the sum of squares within groups, SSW. This partitioning allows ANOVA to compare the variation between the groups to the variation within the groups, forming the basis for determining statistical significance. The SSB reflects the variability between the group means. A larger SSB indicates that the means of the groups are more spread out, suggesting a potential difference between the groups being compared. The SSW, on the other hand, represents the variability within each group. This variation is often attributed to random error or individual differences within the groups. The ratio of SSB to SSW forms the F statistic, which is the test statistic used in ANOVA. A larger F statistic indicates that the variation between the groups is greater relative to the variation within the groups, suggesting that the group differences are less likely due to random chance. Conversely, a smaller F statistic implies that the variation between the groups is not much different from the variation within the groups, making it difficult to conclude that the observed group differences are statistically significant. Imagine you're comparing the heights of basketball players, football players, and swimmers. The SSB would reflect the differences in average heights between these 3 groups. The SSW, however, would represent the variation in height within each group, accounting for the fact that even within a group of basketball players, there will be some variation in height. By comparing these 2 sources of variation, ANOVA can determine if the observed differences in average height between the athlete groups are statistically meaningful or merely due to individual variation within each group.